Spatial isolation uses directional antennas to separate signals geographically, allowing the same frequency to be used in different areas without interference. This technique enhances system capacity. Satellite subsystems are the functional units that make up a satellite, including power supply, communication systems, thermal control, and propulsion. Each subsystem plays a critical role in maintaining overall satellite operation. Satellite architecture and organization refer to the structured arrangement and integration of all subsystems within a satellite, such as communication, power, attitude control, and thermal systems. These subsystems are designed to work together in a coordinated way to ensure efficient operation, proper orientation, reliable signal transmission, and overall system stability throughout the satellite's mission. This is the general block diagram of a communication satellites. In this figure shows a general block diagram of a satellite. All the major subsystems are illustrated. The solar panels supply the electrical power for the spacecraft. They drive regulators that distribute the power to all other subsystems, and they charge the batteries that operates the satellite during eclipse periods. Both DC to DC converters and DE to AC inverters are used to supply special voltages to some subsystems. In this part, the communication subsystem consists of multiple transponders. These receive the uplink signals, amplify them, translate them in frequency, and apply them again for retransmission as downlink signals. The transponders share a common antenna subsystem for the both reception and transmission. The telemetry, tracking, and command subsystem monitors onboard conditions such as temperature and battery voltage and transmit this data back to a ground station for analysis. The ground station may then issue orders to the satellite by transmitting a signal to the command subsystem, which then is used to control many spacecraft functions such as firing the jet thrusters. The jet thrusters and the apogee kick motor or AKM are part of the propulsion subsystem. They are controlled by commands from the ground. The attitude control subsystem provides stabilization in orbit and senses changes in orientation. It fires the jet thrusters to perform attitude adjustment and station keeping maneuvers that keep the satellite in its assigned orbital position. So, the main payload on a communication satellite, of course, is the communication subsystem that performs the function of repeater or relay station. An Earth station takes the signals to be transmitted, known as the baseband signals, and frequency modulates a microwave carrier. The most common baseband signals are voice, video, and computer data. These uplink signals are then amplified, translated in frequency, and retransmitted on the downlink to one or more Earth stations. The component that performs this function is known as a transponder. Most modern communication satellites contain at least 12 transponders. More advanced satellites contain many more. These transponders operate in the microwave frequency range. Communication subsystem is responsible for receiving, processing, and transmitting signals. It includes antennas, receivers, transmitters, and transponders, ensuring reliable communication between ground station and the satellite.
And now we will be talking about single conversion transponder. The term single conversion refers to the fact that only a single frequency translation process from the received signal to be transmitted signal can take place within the satellite. The uplink signal is picked up by the receiving antenna and is first routed to a low noise amplifier or the LNA, usually a GASFET circuit. The signal is very weak at this point even though it has been multiplied somewhat by the gain of the received antenna. So it means that a single conversion transponder performs only one frequency translation from uplink to the downlink. It is the simplest type of satellite transponder. And now we will be talking about the step-by-step operation of the single conversion transponder. Number one is the receiving antenna. It captures the uplink signal from the earth. The signal is very weak due to the long distance travel. Then as you can see next is the LNA or the low noise amplifier. It is usually a GASFET based amplifier that amplifies weak signals and adds minimal noise. Then 3. Next is the frequency converter, the mixer plus local oscillator that converts the uplink frequency to the downlink frequency and prevents interference and feedback between transmit and receive signals. And next is the high power amplifier or the HPA. It boosts the signal to a level suitable for transmission. Then next is the transmitting antenna. It it is the one who sends the processed signal back to the earth. It is also called the downlink. Diplexer, the waveguide assembly that allows one antenna to be shared by a transmitter and a receiver. As you can see, this is the figure of a diplexer. A diplexer allows one antenna to be shared by a transmitter and a receiver. It also acts as a signal separator. Double conversion transponder. All the basic circuits of these systems are similar in function to those of the single conversion repeater. The only difference is that two frequency conversions are carried out. This type of conversion transponder performs two frequency conversions instead of one. And how it works: uplink signal to the first frequency conversion, then the intermediate frequency to the second conversion, then amplified and transmitted. Its advantage is to have a better selectivity, reduce interference and noise, and improve signal quality. The difference between the single conversion and double conversion is that the single conversion only has one mixer and the double conversion has two mixers. Here's a figure of a double conversion transponder. It also has a receiving antenna, LNA, amplifier, BBF, HPA, and BBF, and also the receiving antenna that sends the signals down to the earth. Next, we will discuss about the regenerative transponder. Like the other configurations, it performs the basic amplifications and frequency translation functions, but in this case, the received signal is actually demodulated. Therefore, remodulation is necessary to create the downlink signal. The regenerative transponder has more advanced system where the signal is demodulated, processed, and remodulated. Here's a block diagram of regenerative transponder. Number one is the receive uplink signal, then the amplifier or the LNA, then the demodulator, then then the modulator, the HPA and BPF, and down to the transmit downlink signal. The advantage of this kind of transponder is that it removes noise and distortion, improves signal clarity, and enables the digital processing on board. And unlike other transponders, it does not simply amplify, it reconstructs the signal. Next will be the multi-channel system, a system that permits the transmission of many signals over a single communication channel at the same time by dividing the available bandwidth into smaller channels. It is the bandwidth that is subdivided into smaller channels, and each channel carries separate signals and allows many users to share one transmission system simultaneously. Next is the figure that shows the broadband multi-channel repeater and how it works. Number one, the total bandwidth will be split into sub-channels, and each channels carries the voice, the data, and the video. Then the signals are transmitted simultaneously. In figure 11.23, the processes signals all together as a group, then the entire bandwidth is amplified at once, as you can see on the block diagram. And in this block diagram of the multi-channel receiver transponder, the signals are separated, processed, individually and recombined, unlike the other figure. And the advantage of this kind of multi-channel receiver transponder is that it is efficient to use of bandwidth. Then it supports many users simultaneously and not just once. Next is the power subsystem. A key component of the satellite is its power subsystem. Everything on board operates electrically or has electrical components in it. Most satellites therefore depend entirely upon the power supplies for success. The early satellites used onboard batteries to power everything, but batteries were quickly exhausted and could not be replaced. The life of the satellite is dependent strictly upon the quality of the batteries used and, of course, on the amount of power they drain. The function of a power subsystem is that it supplies electrical power to all satellite systems. Now, the power subsystems use solar panels or the solar array. It is the main power source that converts sunlight to the electricity. Then the batteries, which is the backup during the eclipse or the night periods. Here's a simple figure of a power subsystem. As you can see, there is a stabilized satellite that rotates for the stability and the body stabilized satellite that uses control systems instead of spinning. In a power subsystem, the satellite lifetime depends heavily on the power system's reliability. That's why they are using solar and battery as a backup. Next is a figure of a satellite solar array configuration, spin stabilized satellite, and the body stabilized satellite. Next, we will talk about telemetry, tracking, and control subsystem. All satellites have a telemetry tracking and control, or the TTC subsystem, that allows a ground station to monitor and control conditions in the satellite. The telemetry system is used to report the status of an onboard subsystem to the ground station. The telemetry system typically consists of various electronic sensors for measuring temperature, radiation level, power supply voltages, and other key operating characteristics. Both analog and digital sensors may be used. Then the sensors are selected by a multiplexer and are converted to a digital signal, which then modulates an internal transmitter, and this transmitter sends the telemetry information, which simply means that telemetry tracking and control, or the TTC, are monitors and controls for the satellite operation. Here's a block diagram of a satellite telemetry unit on figure 1127. The sensors measure the temperature, the voltage, and the radiation, while the data is multiplexed, converted to digital, and transmitted to the Earth. As you can see on the block diagram, how it is processed from the receiving into the transmitting.